Hi, and welcome back to The Joy of Ray Tracing, a video series in which we make several ray tracers from scratch. On the last episode, we learned how to intersect a ray with a sphere in 3D, and by the end of that episode, we were able to add a red sphere to our scene, and we were able to move it anywhere we liked. And although it was really cool to get that sphere working in our scenes last time, the appearance of the sphere looked a little flat and dull because it had a uniform red color all over its surface, and it ended up looking like a flat red circle. Well, today we're about to fix that because we are going to learn how to add diffuse lighting and shading to the objects in our scene. And as soon as we do this, our objects will pop out in 3D, and those objects will appear much more realistic, like how we would see them in real life. So I'm super excited to add this feature today. So let's take a look at what we're going to do today. Today's to-dos. Now, before we can add lighting and shading to our scenes, we will need to have surface normals for all the objects that we want to light and shade. And if you recall a couple of episodes back, when we learned how to intersect a ray with a plane, we had to define that plane with its surface normal. So for example, if you have a ground plane like we do in our scene, then the surface normal points at a 90-degree angle to the ground, and so it sticks straight up into the sky. But for a sphere, it's not that simple because the sphere surface is curved everywhere. And so we have an infinite number of normals that stick out from the sphere. And so how do we find the correct surface normal for the point that we're trying to light and shade on the sphere? Well, there's a cool trick that I'm going to show you in a moment. And using that trick, we'll be able to get the exact surface normal for the sphere at that point. And so I'll show you that in a moment. Next, we're going to look at the final part of the dot product operation. And if you recall, the dot product is one of the ways in which we can multiply two vectors with each other. So we've already used the dot product to define a plane a couple of episodes ago. And as we saw, the dot product even showed up in the intersection routine for a ray and a sphere. But today we're going to look at a different interpretation of the dot product. And that interpretation will give us the relationship of the angle between the two vectors. So if you look at their directions, how alike are they, or how different are they pointing? And the dot product will give us this relationship. And the reason we're looking at the dot product yet again on this episode is that we need that interpretation to understand the concept of diffuse shading, which brings us to our next topic that we'll take a look at, which is Lambert's cosine law. First, we'll take a look at the history of this famous law and the physicist who it's named after, Johann Lambert, and we'll see how we can use Lambert's cosine law to apply diffuse lighting to our scenes. Once we get into the code, we'll need to add a couple of new functions to our Vector3 library in JavaScript that we've been building over time. The first one we'll add is called getPointAlongRay. And so this new utility function will be used to give us a point out in 3D space that will be along that ray somewhere. And that'll be determined by the t-value that we give it. And then the other utility function that we're going to add is called multiplyColor. And this is a really simple operation. So you simply take two color vectors that have R, G, and B components and multiply the red component of the first vector times the red component of the second vector, and then do the same for the green components and the blue components. And so it's just a straight up multiplication between the two vectors. And so when we add lighting to our scenes, we'll use this new multiplyColor function a lot, and so it'll be super handy to have. Now, in order to light and shade our scenes, we have to have a light source first. And so for today's demo, we're going to add what's called a directional light source. And a directional light source is probably the most simple type of light source that you can have in computer graphics. All you need is one vector which shows which direction the light is coming from. And the most well-known example of a directional light source is one that we encounter on a daily basis, and that's the sun. So we'll take a look at how to add sunlight to our scenes. And finally, we'll see how everything comes together in our lighted and shaded scene. We'll use the surface normals that we've learned how to calculate for the sphere and the ones that we already have for the ground plane. And then we'll apply Lambert's cosine law to those surface normals and the sunlight direction vector. And then we'll end up with realistic diffuse lighting and shading for all the objects in our scene. So I'm really excited to add this feature today. So let's get started. So I'm going to open up my OneNote app. So first, let's take a look at how to find a surface normal for a sphere at the location that we want to shade. So here we have a sphere in a purple color, and its center is a point I called C. And then I just picked a random point on the sphere, and we call that P. So when we do our ray casting that we learned how to do on the last episode, let's just say that we hit the sphere at this exact location with our ray. And so now that we have this point P on the sphere, and we know for sure that we've hit the sphere with our ray, how do we find this little yellow surface normal that points exactly perpendicular to the surface at that point on the sphere? So I'm going to draw a little 90-degree angle here. So how do we find the exact surface normal for this particular point P that we've chosen on this sphere? Well, it turns out that for spheres only, we can use this cool trick, and it just requires a simple vector subtraction. And so I've written out here to find the surface normal N for the point P that we're interested in. You simply subtract the sphere center C from P. So in other words, P minus C, and then just normalize the result. So the simple formula to determine a normal on a sphere like this is you take the intersection point P, the point that we're interested in lighting and shading, and then you subtract off the sphere center. And so once we do that, we end up with another vector that's pointing in the correct direction. So as you can see here, I've labeled that vector N, and it's in an orange color, because this is the preliminary stage of this normal vector that we're trying to find. So it's not the correct one yet, but once we normalize it, then it'll be correct. So the only tricky thing that you have to remember here is that you have to do P minus C, so the point minus the sphere center. And that'll give you a direction vector going this way. If you do it backwards and you do C minus P, then you get a direction vector going this way, which is the opposite way of what we want. So don't worry if you don't remember that off the top of your head each time you do this, because even I have to remind myself of this little trick, because it's a little counterintuitive. You would think it's C minus P, and then you would get the direction vector going that way, but it's actually the opposite way. So it's P minus C, and then you get the vector going this way. And so even though I've been doing ray tracing for 10 plus years now, I sometimes mix this up. And so don't worry if that seems a little counterintuitive to you and you can't remember that all the time. Once we put it in code, it'll be there, and we'll make sure it's correct. So now that we have this vector N that goes from C to P, we need to normalize it, because although it's pointing in the right direction, it's the incorrect length. So remember, direction vectors have to have a length of exactly 1. And so what we do is normalize that orange vector that we got from C to P. And so we can simply call normalize on this orange vector here, this dotted vector, and then we get the final correct normal vector for the sphere at this location. And so that's in the yellow color here. And so I moved the yellow vector up here to have its tail touch the point P here. And you're free to move a normal vector around the scene anywhere you like, because remember, with direction vectors, we don't care where they're located in the scene. We just care about which direction that they're pointing in. And so as long as this direction vector is pointing exactly where we want it to, we can take this yellow vector and move it anywhere we like. And as you can imagine, you could have this point P anywhere along the surface. So let's say I hit the sphere down here, and now we call that point P, and we simply do this calculation in the exact same manner. So remember, it's P minus C to get a vector going this way. So it's a little counterintuitive, but so it's P minus C. And then you would get an orange vector pointing this way, but it's the incorrect length, remember, so we need to normalize it, and that'll make it a unit length of 1. And so we normalize that, and then we end up, let me move this over just a little bit. And so our surface normal for this location on the sphere would look like that. And we call that vector n. So as you can hopefully see, every point that you can pick will have its own unique surface normal. And that surface normal will point at exactly 90 degrees from the surface. And that'll tell you which way that particular patch of the surface of the sphere is facing. So you can do this calculation no matter where the point is located on the sphere surface. So I think that's a pretty cool trick to finding the normal for a point on the sphere. Now, before we take a look at how diffuse lighting works with Lambert's cosine law, we need to take a look at one more aspect of the dot product. And so you can see on the whiteboard here we have vector u and vector v, and we learned a couple episodes back how to do a dot product between those two vectors. So recall that if you want to do u dot v, you simply take the x component of u and multiply it with the x component of v, and then you add on to that the y component of u, multiply with the y component of v, and then finally add on the z component of u, multiply with the z component of v. So it's basically ux times vx plus uy times vy plus uz times vz. So you just simply multiply all the components together and then add them all up at the end, and that gives you a scalar number. Remember, so it doesn't really give you a vector, it gives you just a plain simple number at the end. And when we first learned about the dot product, we looked at that as kind of like a shadow that vector u casts on vector v. But the more important way of looking at it, now that we're getting into lighting and shading, is that we would like to know the relationship between u and v in terms of the angle between them. So here I've drawn in a pink color an angle, and I labeled that theta. And so that's the Greek letter theta. And that's just the convention of naming angles. Typically in computer graphics, we label the angle between two vectors theta. And it kind of looks like an O with a horizontal line going through it. So for our lighting purposes, we don't really need to know the exact angle. And there is a way to find that angle using trigonometry. But what we're more interested in with our ray tracers is how similar are these vectors in terms of where they're pointing. So we just want to know the general relationship between the two vectors in terms of their directions. And so the final way of interpreting a dot product is with this equation here, which is derived from the law of cosines. And this interpretation or equation states that vector u dotted with vector v is the same as the length of vector u times the length of vector v times the cosine of the angle between them. So that was a mouthful. Let me say that one more time. So u dot v is the same as the length of u times the length of v times the cosine of the angle between the two vectors, u and v. So if you notice, the angle theta is in this equation. So now we can use this to find out about the relationship between the two vectors and the angle between them, or how similar their directions are to each other, or how different they are to each other. Now we can take this equation, which looks a little messy, and take it one step further and simplify it even further to its final form. And this states that if vector u and vector v are both unit length, so they're normalized vectors, then this equation becomes even simpler. Remember that these double bars mean the length of a vector. So the length of u times the length of v. Well, if the length of u is 1 and we normalized it, and the length of v is also 1 because we normalized it as well, then these both become 1s. And so it's 1 times cosine theta. And in algebra, we never have to write a 1 if it's being multiplied with something, because it doesn't change the other number. So the 1s essentially go away, and we're left with this simple relationship, which says u dot v is the same thing as cosine theta. And this is even more useful because if we have both of these vectors normalized, so they're a unit length of 1, then we can simply do a dot product between them. And we already have that dot product, remember, in our vector3 library that we wrote in JavaScript. So we just perform a dot product operation between u and v, and then we automatically get this relationship in terms of the directions of the vectors. And don't worry if you don't remember what this cosine means, and sine and tan and all that stuff from trigonometry, because what this is saying is if you know how to do the dot product, you can get the answer for cosine theta anyway. So you don't need to do any trigonometry at all. And on the computer, even though computers are blazingly fast nowadays, the trigonometric functions like sine, cosine, tan, those are all much more expensive to do than a simple dot product, because the dot product only has a couple of multiplications and a couple of additions. And so computers can go through that really fast. And finally, I wrote this here. Cosine theta is used everywhere when doing lighting and shading in computer graphics. So you'll see this cosine theta term pop up everywhere where you're doing some kind of calculations for lighting. And as we'll see in a future episode, the famous rendering equation, which is a beautiful equation that describes how light interacts with all materials, this rendering equation contains the term cosine theta almost at the very end of the equation. It's a big long equation, but if you look at it closely, you'll see a little cosine theta buried in the equation itself. So this relationship, this cosine theta between the two vectors, is a really important measurement that we'll need to know how to calculate if we want to do lighting and shading in computer graphics. So now on the next whiteboard, let's zoom into this area here and take a look at how this cosine theta can tell us about the relationship between the two vectors. So on the next whiteboard here, I've zoomed into the diagram that we had on the last whiteboard. And so you see the number line only goes from 0 to 1 in the positive x direction, 0 to 1 in the positive y direction, 0 to negative 1 in the negative x direction, and 0 to negative 1 in the y direction. And I've outlined a unit circle here in purple. So now it's kind of like we zoomed way into that diagram that we had on the last whiteboard, and we're only looking at a portion of the graph, so 0 to 1 in all directions. And also you'll see that I shrunk down both vector u and vector v so that they lie exactly on the unit circle. In order to get vector u and v to be a unit length of 1 like this, we just simply normalize both of them. And so when we call normalize on vector u, it shrinks it down and it puts its tip right on this circle. And then we do the same for vector v, and it puts the tip right on the circle over here on the positive x-axis. And remember, when we did that, we simplified that earlier equation, that final interpretation of the dot product, which says u dot v is the same thing as the length of u times the length of v times the cosine of the angle between them. So when we shrunk both u and v down to 1, those lengths in the earlier equation became 1s, and we were able to get rid of those because you don't need to write out a multiplication of 1. So now we're left with u dot v equals cosine theta, and so I've rewritten that over here, and then I've restated what that means. So the dot product of u and v gives the relationship between u's direction and v's direction. So we're only concerned with how they're related to each other in terms of their directions. So are they pointing kind of in the same way, or are they pointing at 90-degree angles, or are they pointing in opposite directions? And so we don't care about length anymore. We're just looking at the relationship in terms of the angle between them. So remember, when we do the dot product, which is just multiplying the x components and the y components and the z components and then adding all those up together to get a number, how does this actually tell us the cosine of theta? So again, don't worry if you don't remember sine and cosine from trigonometry, but trigonometric functions like that, like sine and cosine and tan, they all give us relationships between the edges of a triangle in the case of trigonometry, or in our case here with linear algebra, we're looking at vectors. And so they also can give us relationships between those two vectors. But don't worry if you don't have an intuition for all this, because we really don't need to worry about that. In our ray tracing programs, we're just simply going to use this dot product to find the relationship and then just stick that into our lighting calculation. And it's a very simple calculation. So let's just do some quick examples here so you can see how the dot product will give us the cosine of the angle, or the relationship between the two vectors and how they're pointing. So here's some examples of taking the dot product of u and v in different scenarios. So the first scenario, when we take the dot product of vector u and vector v, and they're in this configuration where they're pointing in the same direction, the angle theta between them is effectively 0. So if you were actually to take a graphing calculator and plug in cosine of 0, you would get an answer back of 1. And that's the maximum value. But the nice thing about the dot product and this interpretation of the dot product is that we don't have to do this expensive cosine theta or cosine 0 to realize that the answer is 1, because all we do is take the dot product of u and v, which is a simple operation for the computer to do, and we'll get back the same exact answer of 1, or the maximum value. And therefore, if we do a dot product between any two vectors, and they're both unit length, and we get back an answer of 1, then we know that u and v are pointing in the exact same direction. So let's look at another example. So this time I drew vector u pointing straight up, and vector v is still pointing to the right. And I don't know if you can see it, but there's a little 90-degree mark in pink right there between the two vectors. So it's showing that they're perpendicular. They're 90 degrees to each other. And so if we knew that ahead of time, if we knew that they were exactly 90, and we took the cosine of 90 in our graphing calculator, we would get an answer of 0. And so what does that mean? Well, if we have two vectors out in the wild and we do the dot product between them, so remember the simple dot product, which is x times x plus y times y plus z times z, and we get back 0, we know for a fact that those two vectors are exactly perpendicular to each other or at 90 degrees to each other. Let's take a look at another example. So this time the green vector u is pointing to the left while the vector v is still pointing to the right. So now they're completely opposite. If you remember from trigonometry, if you increase the angle between two vectors all the way until it hits the x-axis on the other side, then the angle between those is effectively 180 degrees. So if we were to plug cosine of 180 into the graphing calculator, we would get back -1. So therefore, if we do a dot product between any two vectors out in our scene and we get back an answer of -1, then we know that those vectors are pointing in the exact opposite direction. And let's just take a look at one more example. And this time, the vectors are pointing in a similar manner to the diagram here in the middle. So the green vector u is pointing up and to the right, just like it is here, and the vector v is still pointing to the right. And so now they make an arbitrary angle, so we don't know what that angle is. Just eyeballing it, it's probably around 45 degrees or so. But again, the nice thing about the dot product is we don't need to know that angle in advance. It can be any arbitrary angle out there in 3D space. And so let's say we did the dot product between these two vectors in this configuration, and we got back an answer of 0.7. So what does that mean? Well, just by eyeballing this, theta is about 45 degrees. So u is about 45 degrees from vector v. And in fact, if we plug in cosine of 45 degrees into our graphing calculator, we would get back an answer of 0.7 and some other digits. But effectively, we can say it's around 0.7 and just kind of round it to that. So if we get back an answer of 0.7, that means they're kind of pointing in the same direction, but not exactly. And it's a positive number, so we know that they're both going in the same general direction. And so to recap, when you do a simple dot product between any two vectors out in your scene, and they're both unit length vectors, you have to normalize them first for this to work. But when you do that, and you take the dot product, you will get an answer like the ones in yellow here. And it's going to be between the range of -1 and +1. It can't go outside that range. And so right off the bat, if it's 1 exactly, you know that they're right on top of each other. They're pointing in exactly the same direction. And that's the maximum value for the relationship between those two vectors. And then if you get 0 back, you know that they're pointing at 90-degree angles to each other. And then if we get a negative answer for our dot product, that means the vectors must be pointing in opposite directions. And then in most cases, you'll get a number like this, which is between 0 and 1. And so you'll get like 0.7 or 0.2 or 0.5 or something like that. And that means the vectors are somewhat related. The bigger that number is, the smaller the angle. And so the bigger the number that you get back from the dot product means that the more similar they are in their direction. And the smaller value you get back from the dot product means that the angle is getting bigger and they have less to do with each other. So hopefully that gives you an intuitive sense of how the dot product will tell us the relationship of the vectors in terms of their directions. And so the dot product will help us determine how similar two direction vectors are to each other or how different they are, and all gradations in between. All right, so now we're going to take a break from all this math and have some fun by doing some experiments in the real world. And so remember today that our goal is to add diffuse lighting and shading to the objects in our scenes. And so when I say diffuse lighting, what am I actually talking about? Well, as we'll see in the very next episode, there's actually 3 components of light that we need to consider in order to get a plausible looking image. And so the 3 components are ambient light, diffuse light, and specular light. Now, ambient light is sort of an approximation to what really goes on in real life with real objects. ambient light can be thought of as the general ambient room lighting or the environment lighting that's all around us. So for our purposes, we can just consider one type of ambient light that is present throughout the scene. And so every object, no matter which way it's facing or what kind of object it is, will receive this ambient light. And so we'll take a look at that later when we actually add lighting to our demo. And it's really simple. That's the most simple type of lighting that we can add. So ambient light is the first type of light that we are going to consider. The second type is diffuse light. And to be more specific, it's actually diffuse light that comes directly from a light source. So in order to have diffuse lighting, you first have to have a light source. So that could be the sun if you're outdoors, or if you're indoors, that can be artificial lights. And so when we say diffuse lighting, what we're actually talking about is how objects with a diffuse material reflect that incoming light back into our eyes or back into the camera for our ray tracer. And so what are real-world examples of diffuse materials? In actuality, not many materials out there are completely, perfectly diffuse. They might have just a little bit of shine to them or a little specular lighting, as we'll talk about in a moment. But some real-world materials that come close to being perfectly diffuse are materials like chalk. And so when you think of a piece of chalk, its reflection of the light around it is very diffuse and soft. There's no bright highlights where you can see the reflection of the light source in the chalk. It's just kind of like a diffuse, uniform color all over the object. And so I actually have a piece of chalk with me to show you. So this is some street chalk that my kids had when they were little. And so this piece of chalk is in a cylinder shape. And so let me actually turn off, I have two lights lighting up my room here, but I'm going to actually turn off this light. And so we'll only have the light source as being from this direction. And so let's see what that looks like. Okay, so now I've turned off this side light over here and I only have one light illuminating my entire room. And so you can see the reflection of my face. This side of my face that's facing the light is brighter than the side that's not facing the light. And so we can see that on the chalk as well. And so the reason that chalk is used as a material that's almost perfectly diffuse is because there's no shiny highlights on the surface of the chalk. So although my face and the chalk are lit in a similar manner, if you look closely, there's highlights on my skin, like on my forehead and on my cheek and on my nose. And so you can actually see the light in my skin that's being reflected from this direction here. So you get a picture of what the light looks like, and that's called a specular reflection. And so if you look in a mirror, for instance, you're getting only specular reflection. You get no diffuse reflections because the reflections that are coming back into your eye are perfectly reflected. But if you look at this chalk, there's no such highlights. You can't see what kind of light is lighting up the scene. You don't know if it's a circle light or a square light or anything about the shape of the light. All you get is the gradations in intensity of the light. So it's taking that incoming light and then just bouncing it off in random directions, and we get that soft reflection. And so let's take a look at another aspect of this diffuse surface, and that is when I rotate it in a certain way, then we can see that it becomes brighter and then darker. So let's focus in on this top cylinder cap, this circle on the top here. And notice when I point it right at the light, I'm going to try to line this up so you can see. Okay. When I point it right at the light, it's maximum brightness. You can't get any brighter than this because I'm pointing it right at the light source. But watch what happens when I slowly turn it away from the light. So it's a little less, a little darker, a little darker, darker, and I don't know if you can see that very well, like that. So that's the minimum amount of brightness that you can get from this object. And so let me rotate it now towards the light source. So it's getting lighter, 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 and full intensity. So I'll do that a couple of times so you can see how it changes. Now that's a flat surface like our plane that we have in the ground plane in our scene. But if you have a curved surface like this part here, the cylinder part, then you can notice this nice gradation. So it starts with maximum brightness, and then it gets darker and darker and darker, and finally ends up with the minimum brightness over here on this side. And just one more note, there is some light over here, so it's not completely black, and that's because of the ambient light. So the ambient light that's all around my room here is lighting up this side of the chalk, even though it can't see the light source from where this side is. So in a moment, when we go into the code and add in all this diffuse lighting to our ray tracing demos, we'll have to add in that ambient light in order to not have the object be completely black on the side that's not facing the light. And so let me show you one more object that I have with me. And this one's actually a sphere. I couldn't find an exact diffuse sphere, but this comes close. It's a tennis ball. And so you can see, like if I can get it right in the camera there, that it's being illuminated on this side, and it's a little brighter on this side, and it's darker on this side. Let me get it just like that. And you can see the terminator right here. And so this side right here is the brightest that it can be because it's facing directly towards the light. And then it gradually gets darker and darker in a nice gradient fashion. And as you get around here, it can't even see the light source anymore. So it's a uniform shadowed dark color over here on this side of the ball. So the goal for our ray tracers today is to make something that kind of looks like this, where it's brighter on the side that's facing the light, and then it gradually falls off into shadow. And then we add a little ambient light to the scene globally. And so every object will get this little amount of light, and that'll help us to see the objects out in the scene that happen to be facing away from the light. So the question now is, what makes it go from light to gradually darker and darker to dark? What's happening physically in the real world that makes this cool effect, this gradient effect of bright to gradually darker and darker? Well, a physicist by the name of Johann Lambert asked this very question many years ago. So let's take a look at Lambert's important discoveries for the science of illumination. Now, when you do a search for Lambert's cosine law, you might see it under different names. And so it can be called the cosine emission law or Lambert's emission law, but most commonly you'll see it as Lambert's cosine law. And so first of all, let's see a picture of Johann Lambert. And it says here he was a polymath, which means he could do many different things at an expert level, kind of like Leonardo da Vinci. And it says he made important contributions to subjects of mathematics, physics, philosophy, astronomy, and map projections. The one we're going to be looking at today is in the world of physics, and more specifically, optics. And so Lambert published his famous book, Photometria, and here's a picture of the cover. And what's amazing to me is he published this back in 1760. And so that's over 250 years ago that he made these important discoveries about the nature of light and diffuse reflection. So if we look at what Lambert's cosine law is, it says in optics, Lambert's cosine law says that the radiant intensity or luminant intensity observed from an ideal diffusely reflecting surface, like chalk, or ideal diffuse radiator, is directly proportional to the cosine of the angle theta between the observer's line of sight and the surface normal. Now that's a big mouthful there, but you'll notice that it says diffusely reflecting, so that's like our chalk or the tennis ball. So something that has those material properties of diffusely reflecting incoming light. And then it has the function cosine of the angle theta, and we've already seen cosine theta somewhere, right? And then it says between the observer's line of sight and the surface normal. Well, we talked about surface normals. This one is a little confusing because we're looking at it in terms of the light direction and not the observer line of sight. But those can be thought of as being the same type of input to this law. So if you scroll down just a little bit, it talks about Lambertian scatterers. So they use the name Lambert in this identifier of this material. And so these objects here, the chalk and the tennis ball and objects like that, are considered Lambertian scatterers. And that means they scatter light diffusely or randomly. And so now we come to the definition, which is more in line of what we're trying to do with our ray tracers. And so we read here, when an area element is radiating as a result of being illuminated. So an area element is kind of like a point on a surface. So if you take one small point of this chalk and you consider only that little surface patch or that little part of it, like a point in space, that's what they mean by an area element. So when an area element or a point on an object is radiating as a result of being illuminated by an external source, so the light over here, the irradiance or energy or photons landing on that area element will be proportional to the cosine of the angle between the illuminating source and the surface normal. And so what Lambert discovered all those years ago is that there is a proportional relationship between the surface normal of an object and the direction towards the light source. And furthermore, he says that this proportion is in fact the cosine of the angle between those two vectors. So let's take the chalk, for example, and just look at the top circular part of this, the cap of the chalk. And so if we consider the normal pointing this way, straight up, like our ground plane, and then we have a vector pointing from the object towards the light source, which is over here, then the cosine of the angle between those two vectors will give us the amount of illumination falling on this object, or at the exact point that we're interested in on that object. So people back then knew that when you face an object towards the light, it gets brighter, and as you turn the object away from the light, it gets darker. So everybody knows that intuitively, but Lambert actually discovered the physical phenomenon that leads to this lightening and darkening of objects as we turn them towards and away from light sources. And then he was able to make a model of this, and that model is called the Lambert cosine law. And as you can guess, inside the law is the term cosine theta. So he was able to make a mathematical model of this physical phenomenon that we all take for granted every day. And so now let's take a look at a whiteboard where I have the Lambert cosine law written out and explained through some helpful diagrams. Okay, so on this whiteboard, I've restated Lambert's cosine law in a way that relates to what we're trying to do with our ray tracers and adding diffuse light to our scenes. So Lambert's cosine law states that the intensity I of light falling on a diffuse surface is proportional to the cosine of the angle theta between the surface normal N and the direction vector L towards the light. So let's take that piece by piece. The intensity I of light, so that's like the light coming from the sun or a light source in your room, and we're measuring that as the letter I here. So I is the amount of light that can reach the surface. And In particular, it's the amount that can reach the little point that you're interested in shading. So once we get a point back from our ray tracers, when we've shot out all the rays and we're intersecting objects, when we get a surface back, like say a plane or a sphere, we want to know how much light is reaching that particular point on that particular object. And so we're only interested in a little bitty tiny surface patch. It's infinitesimal. It's mathematically infinitely small. So the amount of that light that reaches the object at this location is proportional to the cosine of the angle theta between the surface normal n and the direction vector L. So let's take a look at these last two bits here, the surface normal n and the direction vector L. So here I've drawn out just a little sample diagram of what it might look like. So the surface is down here in purple, and this can be the surface of any type of object. We're just kind of zooming in at that one little location, that one little point that we're interested in shading. So we have a surface sitting flat here, and then we have a surface normal n in this orange color. And that is remember, that is a normalized vector, so it's a unit length of 1. So it's a little tiny vector that points away from the surface, or perpendicular to the surface at a 90-degree angle. And then here's a new vector that we haven't seen before because we haven't added a light source to our scenes yet. But let's say the sun is over here in the sky, and so what we do is go from the point towards the direction of the sun. So that vector, usually in computer graphics, is called L, and that stands for light. And notice too that this L vector is normalized. So it's a unit length of 1, just like the normal vector is. And so for all this to work, all we need is two vectors. We need a surface normal vector that shows which way the surface is facing, and then we have a light direction vector which points towards the light. So even though physically the light is coming from the sun and then going this way in the opposite direction towards the surface, we want to know the opposite direction. So which way to the light? Which way is the light in the scene? So instead of the light to the surface, we go surface to light. And that produces a vector that points out from the surface. So now we have two vectors that are pointing out from the little point on the surface that we're interested in shading or lighting. And then if you can see here, I drew a little angle and I named that theta. And so the brilliant discovery that Lambert made all those years ago is that there's a direct relation between the cosine of that angle, between those two vectors, and the intensity of the reflected light that we see in the end, or that our cameras can see. So now let's put this in more solid mathematical terms. And don't worry, the equation is super simple, which makes it all the more elegant, I think. So what Lambert was saying was that I, the intensity of the reflected light, is the same as cosine of the angle between those two little vectors. And recall from a couple of whiteboards ago that we said that we don't actually have to do this cosine theta business here. We can just do a dot product between the two vectors and simplify things. And so we don't even have to know what the angle is or anything. We just have to have the two vectors supplied, and then we can go ahead and calculate the intensity of the lighting at that point. And so what we do is say I equals n dotted with L. So here's the n vector. You dot this vector with this vector. And remember, the dot product between two vectors returns a simple number or a scalar. And so that will give us the intensity, the scalar value of how much light is coming off of that surface. So I think that's really insightful of Lambert to be able to come up with a mental model like this, or a simple mathematical model of what's going on physically. And as long as we have a surface normal, and as long as we know the direction towards the light, we can simply do a dot product and get the shading for that point on the surface. So you may be wondering at this point, like I did when I first learned about this, that's great and all. It's proportional to n.l, or the angle between those two vectors. But what's really happening physically under the hood that makes that so? Like, why is that the case in the real world? And so part of the genius of Lambert in his photometria book was that he not only came up with this model of how when the light direction interacts with normals of varying directions, he also provided a physical explanation for why this occurs. And so the last part of this whiteboard, I've drawn out 5 different situations in which we can follow his model and see what's going on physically in the real world and why this is so. Why is this the case that it should be related to n.l? So I've copied this diagram 5 times across here. And on the first copy, I moved the sun up until it's right above the surface. So like at high noon, you can imagine. And now the surface normal is always the same throughout these diagrams. So it's the orange one that points straight up. But now if you had to draw a direction towards the light, it would coincide exactly with that normal, right? So the little light vector, or the L vector, would be right in line with this normal. And now for a moment, let's think about it physically. So the light is coming from the light source. And so like kind of like how it is in the real world. So now you can imagine in this case, the sun is directly overhead and it's shining its light downward onto the object directly from above. And I've represented one ray of the sun here as this beam, this yellow beam with some thickness to it. And if you look carefully, I put 4 little measurement lines right in the middle, and it's exactly as thick as the point that we want to shade. You can see here that our point that is going to be shaded through this formula is being given the full amount of sunlight. So it's maximum intensity because it's straight on. The face of the object, or the plane in this instance, is facing exactly towards the sun. So it's getting maximum brightness. And I represented that down here as a solid pink color because that's what we used for the I variable here. So this I relates to this right here. And also I wrote it out mathematically using the simple formula for the Lambert cosine law, which states that n.l equals your intensity. So in this case, since the vectors are the same, they're both pointing exactly up, then n.l will give us back a maximum value of 1. And so therefore, we have a maximum intensity of light falling on this object. And therefore, it'll radiate that back into the environment, and we'll see that as a bright, diffuse reflection. Now, it's a little hard to see, but watch what happens on the next one as we rotate the sun just a little bit in the sky like this at an angle. And now, so if you had to draw that little yellow vector L from the point towards the light, now the 2 vectors are slightly off from each other. And if we do a dot product between those 2 vectors, we will not get the maximum amount. Instead, we'll get something in between. So in this case, we get 0.75, which is less than 1, or less than the maximum. But physically, take a look at these 4 little gray lines here. I kept those the same width, but now we rotated that beam just a little bit, and notice that the areas where that beam hits the ground are a little spread out now. So go back and look at this. You can see the width from here to here as it hits the ground is this far. Now look at this. The width of this one and this one as they intersect the ground are a little farther, just by a little bit. And so due to the conservation of energy, which Lambert was well aware of, that energy must necessarily be spread out a little bit. So the point that we're interested in, right underneath this orange arrow here, has to get just a little bit less because there's there's more surface area that's getting illuminated with the same amount of light. So remember, the light is not changing at all from picture to picture. It's the same beam with the same intensity from the sun. We're just looking at a cross section of it. And so if you angle that just a little bit, now where those parallel lines meet is just a little spread out from the diagram before. That's why when the normal and the light direction vector are a little off, we get less than 1. Now let's keep going with this. So we're going to take the sun and move it farther down. So now it's getting towards afternoon. So now it's getting later in the day. And once again, if we follow these yellow parallel lines, and I kept the 4 little measurement lines in the middle there so that we can see the beam is not changed at all. It's just being angled. So if you trace those lines where they hit the ground here, it's even more spread out now. And so if you were to take the dot product of this normal vector, which hasn't changed, and then the new L vector, which is over farther this way, then you would get something like 0.5. So now we're talking about half intensity of what it was. And now it gets even more extreme as we get into sunset. So now we move the sun way down by the horizon. And once again, I have all these little measurement lines in between. So I have 4 little gray lines in between to show that the width of the beam has not changed at all. It's not getting wider. It's just rotating. But look at how the parallel lines of the beam's edges, the yellow ones, look at where they intersect the ground. Now it's really wide, so it's all the way over here to here. And we started out with just here to here. And that was like maximum intensity because the light was focused on a certain point. But now it's much more spread out between these 2 edges of the beam. And then if you were to draw an L vector from this point towards the light, it would look kind of like this. And it's almost 90 degrees. So it's like kind of like that. And if you did a dot product between those 2 vectors, you would indeed get 0.25, which is really low intensity. And so that surface would be much darker. And now let's take it to the extreme, and we're going to put the sun directly right below the horizon. Now, I couldn't really picture that correctly on this because the sun would have to be below this plane here, but like you can imagine the sun being right on the edge of the plane like that. And so now the sun rays are coming parallel with the plane, essentially. And so if we did a dot product between the normal vector, which hasn't changed, and the new L vector, which is to the right, now we have a perfect 90-degree angle. And you remember, if we have a normal vector and another vector, and you have those as 90-degree angles from each other, when you take the dot product, it'll equal 0 because those vectors don't have anything to do with each other. One's going up and one's going sideways. And so in fact, when we do the dot product between the normal vector and this L vector, we indeed get 0. So in other words, no light is reaching the surface at all. So as your eye moves from diagram to diagram, so as we go from 1 through 5 here, you can see how the intensity marked in this pink color gradually falls off to 0. So it starts out as full intensity, then a little less, then a little less, a little less, and then finally 0 or nothing. And that's just because we're moving that L vector sideways like that. The normal vector is just remaining still. Now the cool thing is that you can move the L vector like we did here, but you can also keep the L vector the same, but move the normal vector or the surface. So that's like when I demonstrated before with this chalk. If you look at the top surface, the top little circular cap of this chalk, and I keep the L direction the same. So the light is over here and I'm not moving that light source at all. It's just sitting there. But now I'm going to move the N vector. So the N is pointing towards the light like that. And so at this point, the N and the L vectors are the same. And that's why we get maximum intensity. And you can see that bright spot right here. But now as I rotate that normal vector away from
perfectly parallel, it gets darker and darker and darker, and finally maximum darkness. And this down here, these diagrams show physically what's happening. So when you have a surface pointing right towards the light, it's maximum intensity because per area, you're getting the maximum amount of light. All the light is being concentrated on a tiny little spot. And that's why at high noon, if you're in certain areas of the globe, you'll feel it is really, really hot. And so the hottest point of the day is when the sun is directly overhead. You're getting that direct radiation in its full intensity. And then as the day grows long and as the sun starts to set, then the intensity gets less and less. And we feel that in the temperature as well. That's why it kind of cools off towards the evening time. And it's all due to that fact that the light beams are being spread out over a larger and larger area as you increase that angle. So this relates back to what Lambert discovered all those years ago, and that he said if you take the normal vector of a surface that's 90 degrees to the surface, and then you make a vector from the surface towards the light, and you do a dot product, and you find the cosine of the angle between those two vectors, which in our case is a dot product, it's a simple operation for the computer, then you find the intensity of the light that's reflected back to our eyes. And I think this is a really cool thing in computer graphics, that we can use such a simple formula, like all we have to do is a one dot product and we get our lighting. And so I think it's really fascinating that Lambert was able to boil it down to that simple of a formula and to accurately model what's going on in the real world with diffuse objects. So now let's take a look at the final whiteboard for this episode, and that's going to show how we can actually use this cosine law, or this n.L lighting, in our ray tracers.
Okay, on this last whiteboard, I'm going to try to bring everything together that we've learned today on the previous whiteboards and outline step by step what we need to do if we want to add diffuse shading to the objects in our ray traced scenes. So over here on the right, I've drawn an example scene where I have a sphere out in the scene and then a light source, such as the sun, up in the sky and over to the right a little bit. Now you have to imagine that there's a screen right here over this entire scene. And for each pixel, we send out a ray through that pixel out into the scene and see if we hit anything. So if we just go from left to right like this and scan the screen, none of these pixels would hit the object. And then as we get lower and lower, all of a sudden we hit the object here. And so let's say we got a positive hit from one of our rays. Let's focus in on this pixel right here. The ray sphere intersect function that we wrote last time only gives us back a t value for this ray that hit the sphere right at this point P. And so we don't actually know what that point P is. We don't know where it's located in 3D in the scene. And so our first step is to locate that point P in 3D space along the ray that hit the object. And so at the beginning of this episode, when we looked at our to-do list, that was why I had add getPointAlongRay to our 3D vector JavaScript library. So once we add that simple function, we'll be able to get this point along the ray where the ray actually hit the sphere. And so once we get that point along the ray, and we'll call that point P, then we can proceed to find the surface normal for this sphere. And if you recall from the first whiteboard, we learned how to do that using the point of intersection and then the sphere center. So we subtract the sphere center from the point of intersection, P minus C, and that gives us a vector pointing in the direction of the normal, but we have to normalize it to a length of 1. So we call normalize on that new vector, and that gives us the vector n that we need. And also remember, we need a vector towards the light source. So where is the light coming from? And so we need a vector going from P towards the sun or the light source in your scene. And so when we get those two vectors back, the surface normal and the light vector, we have everything we need. So now I've drawn in the surface normal N, and that's what we got when we subtracted off the sphere center and then normalized the result. So now we have a correct surface normal vector N. And then we ourselves will define this L vector, this direction towards the light. If we want it to be up in the sky and over to the right, we'll just define that with its 3D vector. And so we will define this L vector here ourselves. We don't need to calculate that. So once we have the vectors that we need, the surface normal N and the direction towards the light L, then we're ready to apply diffuse lighting and shading to this point. So over here, I wrote what we need to do to get the final point's color at this location, this point P here. So to get a point's color on a diffuse object, like this object here, multiply the object's RGB color by the light's RGB color, scaled by the Lambert cosine term, or N.L. Let's take that piece by piece because that was saying a lot there. To get a point's color, so this point P will have a final color in our lighted and shaded scene. So to get that color on a diffuse object, and remember a diffuse object is one that randomly scatters the rays and gives off a nice soft diffuse reflection of the light that is shining upon it. So a surface like this chalk or the tennis ball that we looked at earlier. You multiply the object's RGB color. So remember last time we defined our sphere as being a pure red color. So we're going to take that color that we defined, this RGB color, this red for this particular sphere, and then multiply that with the light's RGB color, because our light can have its own color. And so typically for sunlight and bright light sources like that, you'll want it to be all white, like a pure white color. Although I drew this as a yellow sun here, we're actually going to make that a pure white in our scene. So it'll have a red component of 1, a green component of 1, and a blue component of 1. And so that'll give a pure bright white color to our light source. So we take the object's color, this red sphere, and then multiply it by the light color, which is a pure white. And that's why on the to-do list, we also had a to-do of adding a color multiply function to our Vector3 JavaScript library. But that's a really easy function to add. It's literally just multiplying the R times the R, and then the G times the G, and then the B times the B. And so after doing that simple multiplication, you're left with a new vector that has 3 components that is the product of those 2 colors multiplied against each other. And then finally, we scale this new color that we got from the multiplication by the Lambert cosine term, using the Lambert's cosine law that we learned about on the previous whiteboard. And so remember that was, we take the dot product of the normal vector with the light vector, and we get that intensity of the light that's reflected off the object back into our eyes. And so now that we've detailed all these steps, let's write it out in a more formal way. So this is kind of like in a pseudocode. It says to get the point's final color, you take the object color multiplied with the light color, multiplied with the normal vector dotted with the light vector. And so this point color here is an RGB color. So it'll give you back a final RGB that you can use to correctly give the appearance of lighting and shading to all the objects in your scene. You do this on a per pixel basis. So every pixel that shoots out a ray and hits something, we have to do this simple calculation. So for every intersection we get back, we take the object color that got hit. So in this case, it's a red sphere. and then multiply that by the light color, which is going to be a pure white in our scene, and then scale that or multiply that by the dot product of the surface normal and the direction towards the light. So this little N vector and this little L vector, we take the dot product to get the relationship of the angle between those, and then scale these colors that got multiplied together. And that'll give us the final shaded color of the point that we're interested in. And so if we take one more look at our tennis ball here that we're trying to replicate with our ray tracers, this part of the sphere is bright, and then as you go around, it gets darker and darker until you get to the most dark part on the backside of the sphere. And so you can imagine as we ray trace the scene, we're going to be hitting the sphere at various locations, and for every single point that we hit with a ray, then we're going to calculate the normal for that point. And so you can imagine these little normals are going to go like this all around the sphere. There's an infinite number of those little normals. And so when we calculate this orange normal here, we do that only for the local point at that exact location. And then when we get the normals for all those points that we hit, it'll end up having normals that stick out all over the surface of the sphere. If you can imagine those little bitty normals sticking out from the sphere all around the sphere and exactly perpendicular to the surface at that location, then you can see now why this light has a gradient from bright to dark. And so the normal over here is pointing exactly at the light. So it gets the maximum amount, or 1. And then as you rotate that normal away from the light source, then it falls off gradually and gradually until you get to a 0 value or no light at all. And so if we do this correctly in our ray tracers, we'll get this cool shaded effect where we have all those little tiny normals giving us back different results as we move across the sphere. And we'll get the correct appearance in the end of a 3D sphere like this, where it has that nice gradient shading across its surface. And I just wrote this out in a more succinct form here. So this is saying the same thing, but it's just a little shorter now. So it uses the letter P for the point color here. So this is the same, equals object color times light color times n.l. So you can read this as the final color of the point P equals the object color that was hit times the light color times n.l, or the surface normal dotted with the light direction vector. And then I just gave a little reminder here because all these slides will be available on GitHub, so you can always get back to these whiteboards and review them on your own. And so after every episode, I always put all these whiteboards and diagrams on the Joy of Ray Tracing GitHub repo, so you can always find that. And so I just restated that when multiplying two RGB colors, simply multiply the R components, the G components, and the B components with each other. And so here we have the object color. I wrote that as O. I just shortened the name of the color here. So object color is O, and then the light color is L. So the red channel of the object's color times the red channel of the light's color. And then you take the green channel of the object's color times the green channel of the light's color. And then the blue channel of the object's color times the blue channel of the light's color. So it's red times red, green times green, and blue times blue. And that'll give you back a final color vector, which is the result of multiplying those two colors with each other, such as the light and the object color. And then I put it in the form that we're going to see it as, because remember, we don't really have .r, .g, and .b for our 3D vectors. And so when we implement this color multiply function, ours is going to look like this. So it'll take the x component of the first color times the x component of the second color. So O.x times L dot X, and then O dot Y times L dot Y, and then O dot Z times L dot Z. So although it'll look a little different in our code like that, it'll look like X times X, Y times Y, and Z times Z. We're going to take that and interpret it as R times R, G times G, and B times B. And then we'll get that final color vector back. And so that wraps up everything we need to know about diffuse lighting and shading. And although we went into the history with Lambert and his cosine law, and then we took a look at what's physically happening under the hood when you move around the N and L vectors, once again, it all boils down to a simple little formula that we can just add in our code. And so I think it's kind of cool that we're going to be able to apply Lambert's cosine law and get realistic diffuse lighting for all of the objects in our scenes by just implementing this simple equation here, this object color times the light color times N dot L. And so with that simple diffuse formula, we'll be able to correctly light and shade all the objects, and those objects will really start to pop out in 3D, as you'll see. So I'm really excited to add this diffuse lighting and shading to our ray tracers. So let's head into the code and do that now. So let's open up Visual Studio Code. And we can see what we were working on last time. We had just added the ability to intersect a sphere with a ray and draw that sphere on the screen. Now, before we create a new demo for today, let's go into mathutilities.js, mathutils. And first on our to-do list was to add those two new functions called getPointAlongRay and multiplyColor. So since multiplying colors is fresh in our minds from the last whiteboard, let's do that function first. So scroll up until you see the simple math operations on the vectors, such as subtract and add. And actually, we can just take one of these and copy and paste it, and then just change the addition to a multiplication. That's all we're doing. So let's take this vector3 add function and just select the code for that, Control C, and then go under multiply scalar, go beneath that just a little bit, hit enter a couple times, and Control V to paste. And I'm going to scroll up. Let's first of all change the name. So instead of add, we're going to call it multiplyColor. And just to be absolutely clear, let's change the name of the parameter, which is other vector, to other color vector. So that when we call this function, it'll remind us that we need to supply a color vector instead of just a normal 3D vector. And you'll notice that it went gray when I changed the name. So now we need to change the names of all these as well. So let's do that. And as soon as I do that, this turns white again. And now all we have to do is change the plus signs to multiplication signs. So change the plus to times and do that on each line. And we're done with that function. So that was a really easy one to implement. Now the reason we didn't have this function to begin with, back when we had stuff like add vector, subtract vector, why didn't we have just multiply vector? Well, if you recall, in linear algebra, it doesn't make sense to just simply multiply two vectors together like that. So if you just take the x times x, and then y times y, and then z times z, that doesn't really make sense in the world of linear algebra. But now that we're adding diffuse lighting and shading, we need the ability to multiply two RGB colors. And we represent a color vector, which is RGB, as a normal vector, which is x, y, and z. So although these say .x, .y, and .z, we are going to interpret them as .r, .g, and .b. So our multiplyColor function will have a vector 3, and that will be a color with r, g, and b components. And then when we call multiplyColor on that color vector, it'll take in another color vector, so we can put like the light color in here or something, and then it'll multiply those two colors together, and then we'll get a resulting color. And so we'll definitely use this function today and everywhere in our future ray tracers. The ability to multiply colors like that is very important when you're dealing with lighting and shading. Okay, and so now let's add the getPointAlongRay function. And so let's scroll down just a little farther and go below the mix function here and hit enter a couple of times. And before we add this, let's just recall what getPointAlongRay entails and what it means to get a point out in 3D space along a ray. So I'm going to go back into my OneNote app. And I'm just going back to this ray sphere intersection whiteboard for a moment, just to take a look at a particular spot and take a look at this, the ray equation. And so the ray equation says that a point along the ray equals the ray origin plus a scaled direction of the ray. And we scaled the direction with a value called t. And recall that the t value is how far we went down the ray's direction. So if t is small, then you stay right near the origin of the ray. You don't go very far. But as t gets longer and longer, then we start to go out along the ray's direction, and you can have t be any number you like. So as far as you want to go along that ray. But in particular, look at this next line here, where we break open these vectors into their individual components. And so this is the part that we need right here. So what we did is we took the point P, which is an X, Y, and Z location in 3D space. It's just a point in space. And we took only the X component, and then we took the ray origin, which is also a point in space, and we took its X component, and then we kept the T the same, but then we took the ray direction, which is a direction vector. It's a tiny little vector of length 1. It can point in any direction. And we took only the X component of that as well. So now it reads Px equals Ox plus T dx. That'll give us the X component. And so then we just repeat that for the Y component and the Z component. So now we have Py, or the point we're wanting, is equal to Oy plus T dy. Then we do that once more. Pz is equal to the ray origin Z component plus T times the ray direction Z component. So what we have to do if we want to get a point along a ray, and we're about to add this to our vector library, so our function will be called getPointAlongRay. It's going to take in, it needs 3 bits of information. It needs the ray origin, which is a 3D vector, a 3D point in space, and then it needs the ray's direction, so which way is it pointing, and that's also a 3D vector. And then it needs a t value to scale up and down that direction. So if we supply it with those 3 bits of information, then we should be able to get a point along the ray based on how big the t value is. And so let's go implement that now. Okay, so let's type vector 3 dot prototype, because we're adding to its prototype, dot, and then we're going to call this getPointAlongRay. Get, capital P, point, capital A, along, capital R, ray. getPointAlongRay. Add a space and then equals, and then the keyword function. And all functions need parentheses, so opening parenthesis, and it'll close it for you. And now remember what were the bits of information that it needs to do its work. So we need a ray origin, we need a ray direction, and we need a T value for that ray. So let's add those parameters now. And so the first one is ray origin. And then they're separated by commas. So comma, space, ray direction, comma, space, and then T. And that should be all the information that this function will need to do its job. And now go to the end of the line and hit enter and opening curly brace, and it'll close it for you, and hit enter once more. Oh, and before I forget, let's add the semicolon after this statement, because this is kind of like a statement or an expression in JavaScript. You're setting this member of the prototype equal to a function. It's kind of like you're doing an action in JavaScript. So technically, after the end of this curly brace here, we need a semicolon. And now this reads as a statement. So again, you don't really need those semicolons for your programs to work, but I just like to be really consistent with my semicolon placements. And so now let's go inside the function body and add the first line. And remember, we're breaking apart the 3D vector into its individual components, X, Y, and Z. And then we do a little mathematical operation on each of those components one at a time. So let's start with the X component. So this dot X equals, and then the simple formula was origin X plus T times direction X. So let's implement that. So ray origin dot X, and you can see that highlighted the ray origin. Now it's being used. Plus T times ray direction, and only its X component. So now all the parameters are highlighted. We're correctly using them all. And now I like to add parentheses around this multiplication here so that it gets done first. Let's select the T through the X here, and then just type opening parenthesis. And Visual Studio Code will automatically put the parentheses around the parts that you want. And so this just ensures that the T times ray direction X gets done first, and then it's added to the ray origin X over here. Now, with most programming languages, the order of operator precedence will take over, and it'll go ahead and do the multiplication first and then the addition last, just like we learned in math class. But I always like to make my intention clear with what the formula is doing. And I think adding parentheses to this part here is showing someone that might be reading your code for the first time that you're wanting to do that first and then add the result to ray origin.x. So I just think that's a helpful way of writing this, even though it's not strictly necessary. And now that was a statement in JavaScript, so we end that with a semicolon. And now all we have to do is copy and paste this 2 more times and just change the components. So let's select this line, copy and paste on the next line, and go ahead and paste it again a 3rd time. And now we just change the x's to y's. So y, and then y here, and then y over here. That takes care of the y components. And now let's do the same for the z components. So that becomes z, this becomes z, and this becomes z. And then go on to the next line, and we're going to return this. So that'll give us back the 3D vector or the 3D point that we're wanting. So return this point, this, and then semicolon. All right, I'm going to scroll up just a little bit.
And so if we go back to our whiteboard, we should have px equals ox plus t dx, py equals oy plus t dy, and then pz equals oz plus t dz. So if we go back into the code, px equals ox plus t dx, py equals oy plus t dy, and then pz equals oz plus t dz. So although I'm using just the first letter of the names, you can kind of see how that's exactly what we had on the whiteboard. It's just more spelled out in our code. And now we'll have the ability to get any point out in 3D space where the ray actually hit an object. And so let's say if one pixel's ray that we sent out hit the sphere at the top, let's say, and we want to know exactly where that occurred so that we can do the surface normal calculation that we needed to do for the lighting. So all we have to do now is create a new 3D vector and call it like intersection point or something, and then we call this function on it. So we say intersection point dot getPointAlongRay, and then we supply it with the ray's origin, the ray's direction, and the t-value. And remember that we already have this t-value because that's what all of our intersection functions are for. So when we wrote ray intersect plane and ray intersect sphere, they gave us back the t-value for that ray. And so we can use that now to feed into this getPointAlongRay function, and then it'll give us the exact point where that intersection occurred. So this is one of those really useful functions that we'll use all the time in our ray tracing programs today, as well as our future ray tracers. Okay, and with that, we're done with what we need to do in this mathutilities.js file. So now, what do you say we make a new demo and add our new diffuse lighting and shading features to our scene? So let's go ahead and create a couple of new files that'll hold this demo. So either click on intersectsphere.html here, or you can click on it over here in the File Explorer. Just make sure that you're in that part of the folder, and then click on the new file icon up here. And let's name this new demo Diffuse Lighting .html, and then hit enter, and that will create a new file for us. And then let's go into our web page from last time, which is called Intersect Sphere, and then select all that code, copy it, and go back into diffuselighting.html and paste. And before we go any farther, let's go ahead and change the title so we don't get confused later. So erase intersect sphere and just name it Diffuse Lighting. And then we'll go back in a moment and fix all this because these are going to be pointing at the wrong files, but we'll go ahead and do that in a moment. And now click on intersectsphere.js, which is the file we did last time. And you can also click on it over here. Just make sure you're in the JS folder now. And then likewise, click on New File. And now we're going to add a JavaScript file with the same name as our HTML file that we just created. So let's name it Diffuse Lighting.js. And then hit enter. And that will create a new file called diffuselighting.js. And now go back into intersectsphere.js. And since this one's a longer file, you can just go up to Selection and Select All. That selects all the code for this file. And then now Control-C to copy. And then go back into diffuselighting.js and Control-V to paste. Now, after I do something like this, I always like to click out of the old files so I don't accidentally update those files instead. So go to intersectsphere.html and click X to get rid of that. And then likewise, go up to intersectsphere.js and X out of that. And now we should be left with diffuselighting.html and then raytracingstyles.css. Now this one I just have up there, but we're actually not going to work on that for a long while. But I just have this one up there, but you don't really need it now in our open tabs. And then we should have diffuselighting.js and mathutilities.js will be open because we just worked on that. All right, so the first thing we need to do is go into diffuselighting.html and update this path here because right now it's pointing to the wrong file. So click inside the quotes there and then erase everything up until JS. And now you know this, one of my favorite features of VS Code, when you type / I just love it. Click on diffuselighting.js and it fills it in for you. And now it's pointing to the right file that we just created. So at this point, we're done with this diffuselighting.html file. And now we can just focus on the diffuselighting.js file. But before we start that, let's go ahead and open this up and make sure everything's working. I always like to double check when I do a lot of copying and pasting like this on a new demo. So just let's make sure everything's working how we expect. Go down to the bottom right here and click on Go Live. And that should open up your live server. All right, cool. So that's what we had last time. And so we added the ability to raycast a sphere in 3D. And although I was so happy to get this working last time, and we did a whole bunch of math on the last episode, remember? But the coloring of the sphere leaves something to be desired. You can see that it's a uniform red color all over the surface of the sphere. It doesn't really look 3D. It looks kind of like a flat disc or a circle. Well, we're about to fix that. So now we're going to work on adding our diffuse lighting and shading to this sphere as well as the ground plane. And you're going to see how it's going to just pop out of the page. It's really cool. So everything is working correctly. And let's go back into VS Code and click on diffuselighting.js. And let's scroll all the way to the top. And before we add our diffuse lighting calculations, I'd like to do just some real minor housekeeping on this file. So the first small change I would like to make is renaming this color vector to pixelColor. And so before we had this color vector representing the final color of the pixel, but I don't think that's a very descriptive name. And so let's rename this to pixelColor. I think that'll be a more appropriate name. And someone who's reading this code for the first time will see that that's the final pixel color and not just some color vector that's random or something. Click on the name and erase color vector and rename it to pixelColor. Now by doing that, we're going to mess up later where we use the word color vector. So let's go and find those occurrences and change those as well. And actually, you probably already know this, but you can just search and replace inside of VS Code. And so let's try that now. Go under Edit and then Replace. And we want to find all the occurrences of color vector. So color vector. And it says that there are 8 occurrences, and we want to replace that with pixelColor. And now there's a little button right here that's replace only one entry. We want to replace all occurrences all through the file. So let's click on this button to the right here. It says replace all. And with that, it replaced all the occurrences to pixelColor. And now if we scroll down to the bottom, and take a look at where we actually fill the tiny rectangles that fill up each pixel on our screen, it should read pixelColor.x, pixelColor.y, and pixelColor.z. And remember, we interpret those as X is red, Y is green, and Z is blue. So pixelColor.r, .g, and .b. And that's a minor change, but I just think it reads a little more clearly and what our intent is and what we're doing at the end of this program, which is assigning a color to the pixel. Okay, now scroll up to the top again, or near the top. And the next small change I want to do is changing the ground color to a slightly darker gray. And so instead of the ground color being 0.5, 0.5, and 0.5, let's make it 0.4. So change the 5 to a 4, 5 to a 4, and 5 to a 4. The next very small change I'd like to make is moving the sphere back just a little bit. And so if you go under sphere position, it currently reads -10 in the Z direction. And remember, the more negative something is, the farther back in the scene it is. And so I want to change that to a -15. So let's do that now. And that'll just push the sphere back 5 units. And we're about to increase the zoom of our camera just a little bit. So this will all make sense when we take a look at it in a moment. And then the final housekeeping change that I'd like to make is, as I just mentioned, changing the field of view just slightly and zooming in the camera ever so slightly. And so the objects will appear just a little closer. And that's why we just moved the sphere back a little bit, because we're about to bring everything a little closer to us. And so scroll down to the draw function here, and it has the double for loop. And then keep scrolling until you see ray direction, where we set the ray direction. And currently it reads canvas X, canvas Y, and then -1 in the Z direction. And so we're also going to increase this slightly. And it's a little counterintuitive, but the more negative that value is, the closer the zoom will be, because it'll be seeing less of the scene. And so what we do see will be magnified a little more. And so it's kind of like we're zooming in just ever so slightly. So let's change this. Instead of -1, we're going to put -1.5. And that will just bring everything a little closer and kind of zoom in just a little bit and focus on the sphere more. And that's why we had to push the sphere back just a little bit. So now it'll sit nicely in the middle of our scene. So now with those small changes, let's go and take a look at what we have so far. So go back into the web page. And so as you can see, not much has changed, because what we did essentially is move the sphere back, but then zoom in the camera. So it kind of offset each other. But changing that 1 to a 1.5 in the camera Z will make it so objects appear less distorted as they get on the sides of the screen. So as they get to the right and the left of the screen, they'll be a little less distorted. If you remember last time when we moved this red sphere all over the place, when it got to the edge, it was like almost an ellipse. It was so squashed looking when it got to the side. So this will help just a little bit by changing that 1 to a 1.5. We kind of brought the sides of the screen in, and then we zoomed in the rest of that field of view. And so everything's going to appear closer now and a little less distorted. So let's go back into the code. And now the first thing we need to do if we want to add lighting and shading to our scene is add a light. So let's add a light source, and we're going to add what's known as a directional light source. And so the most famous example of a directional light source is the sun that we see every day. Although the sun is essentially a ball of hot gas, Earth is so far away from the sun that by the time the sun's rays hit the Earth, they're essentially parallel. So in other words, all the objects that we place in the scene, their sense of where the sun is located in the sky should be all the same. So if you're in the same geographic location, as someone else and you both look up towards the sun, then you should be looking exactly in the same direction. Now, that doesn't apply if you're on opposite sides of the globe, obviously, because on one side, if you look up at the sun, it may be in a certain part of the sky, but on another part of the globe, the sun may have already set or something like that. So, but this applies to one single scene. And so we're just ray tracing a little scene, or like a little part of the Earth. And so for all the objects out there, effectively the sun is coming from one direction, and that is a single direction vector. And so all the rays that are coming from the sun at that location in our scene are essentially parallel. And so we can just consider one vector as being towards the sun. So now let's go up and add that sunlight direction vector. Let's scroll up and go underneath where it says let t and let nearest t. So click there and then hit enter a couple of times. And now we're going to create a new 3D vector. And so how we do that is we do let, and let's call this direction to light. So where is the light in the scene? If you had to point towards the sun, which way would you point? So direction to light. And I'm going to scroll up just a little bit. Equals new vector 3, and it should pop up, and then opening parenthesis, and it reminds us it needs an x, y, and z component of that vector. So for now, let's just do something simple and apply 1 to each component of this vector. So we're going to have an x of 1, a y of 1, and a z of 1. So if you remember how the 3D coordinates work, x goes to the right, so it'll place it to the right a little bit, and then y goes up, so it'll place it up like this, and then z goes towards us, so it'll place it back behind our heads, essentially. And so the sun will be slightly behind your head on the right side and up. And that way it'll illuminate the scene from behind our camera or behind our head, and then we'll be able to see the objects. So we're going to give it an x of 1, a y of 1, and a z of 1. And then end that with a semicolon and hit enter. Now, one thing we need to do right away before we can use this direction vector is that, remember, we need to have all directions normalized. And so if a vector represents a direction of any type, we need to make sure that it's a unit length of 1 exactly. So we need to call normalize on this right away before we try to use it in our lighting calculations. So let's call direction to light. You can hit enter as it pops up. Dot normalize. And you can click on this. And then normalize is a function, so it needs parentheses, so opening parenthesis. Now it doesn't take any parameters, it just operates on the vector itself. So we can just hit semicolon at the end and we're done. And so now direction to light will be a unit length vector. It will have a length of exactly 1. So no longer do we care about how long it is, we just care about which direction it's pointing. And just so you recall, this vector was the L vector back on our whiteboards earlier, where we took the dot product between the surface normal vector and the light direction vector. So n.L. So this direction to light vector is the L vector that we had on the previous whiteboards. And now, as I previously mentioned, we need a RGB color for this light. So what color is the sun? And so typically what ray tracers and graphics programs do to handle a bright light source like the sun is just assign it an RGB of maximum value, so 1, 1, 1. And so that'll give it a pure white color. So although in children's drawings and even adult drawings, when you draw the sun, usually you use a yellow color, right? But it's actually white light. It's actually pure white light that is emanating from the sun. The light that we actually receive and the light that we're going to be dealing with here in our ray tracers and our future path tracers is essentially a pure white light. So we should have an equal amount in the R, G, and B channels. And so let's create that sunlight color now. So let sunlight color equals, and this is a vector 3 also, but it's a color vector now. So it's going to have X, Y, and Z components, but we're going to interpret those as R, G, and B. So let's do new vector 3, opening parenthesis, and now we're going to assign it an R, G, and B color. So let's do one for the red channel, one for the green channel, and one for the blue channel. And then end that with a semicolon. And now hit enter a couple of times. And let's add another color now, and we're going to call this one diffuse color. This will represent the contribution of the diffuse color to the objects in our scenes. So let diffuse color equals, and likewise we're going to do new vector 3, but this one we don't have to define because we are going to calculate this later when we loop over all the pixels. New vector 3, opening parenthesis, but now just leave it blank. We don't need to define this. Semicolon. Hit enter. And now remember that when we looked at the Lambert cosine law, it gave us back an intensity of the light. And so that intensity was just a simple number. So let's create a variable now, but it's just going to be a simple number, and let's call it diffuse intensity. And so let diffuse intensity equals, and then let's go ahead and initialize this to 0. We're going to recalculate it later when we do the diffuse lighting and shading anyway, but let's just set it to 0 for now. So 0 and then semicolon. And that diffuse intensity number relates back to the intensity that we found when we did the Lambert cosine law, or the n.L operation. And remember, the dot product gives us back a simple scalar number. So we're going to name that scalar diffuse intensity. Okay, and now scroll down to where we're intersecting the objects in our scene. So we have intersect sphere here and then intersect plane there. I'm going to move this over just a little bit. So currently we are just assigning the pixel color to be whatever the object color is. So pixelColor dot copy sphere color, or pixelColor mix the ground color with the background sky color to get the fog. And so what we're essentially doing here is just lighting up the pixel color with whatever the object color happens to be, whether that be the ground plane or the sphere. But that's not very realistic because it's kind of like the objects have their own light or their own color that they're just emitting on their own. We don't have a light source shining on them yet. And so what we're going to do is remove this pixel color copy here and instead make a more general solution to this intersection and lighting problem. We need more of a general notion of an intersection and its data. And so what I'd like to add now at near the top of our JavaScript file here is a couple of variables that will hold the intersection data. And so what do we need? Recall we need an intersection point out in space. So where did the ray hit the object? And then we need an intersection normal of that intersection point at that particular location on the object. And then finally, we need the intersection color. So what color is that intersection? If we hit the ground, it should be a gray color because that's what we defined the ground to be, is a medium gray color. But if our ray hits the sphere, since it's a red sphere as we defined it, the intersection now should record a red color. So we want to have this kind of running record of all the data associated with that hit point or that intersection point. So let's scroll up again and we're going to add a more general notion of intersection data. And so we'll define a couple of variables and they'll hold all the data associated with whatever intersection has occurred with that particular ray. So let's go up to where it says let t and let nearest t, and then go right underneath those, hit enter. And I'm going to put it right here since the t relates back to the t of the intersection. So how far did the ray go before it hit something in the scene? So this seems like an appropriate place to put all these intersection data variables. And so we need 3 vector 3s. One to hold the color, that's a vector 3 or an RGB. And then we need an intersection point, so that's X, Y, Z, and that's also a vector 3. And then we need an intersection normal, which is also a vector 3, which is a direction vector. Let's create these 3 new vectors now. So let's call this intersection color. So intersection color equals new vector 3. And we don't have to initialize any of these because we're going to calculate them for each and every pixel. So opening parenthesis and then just type semicolon at the end of the line. And now just select this entire line, copy it, and paste it 2 more times below. So let's call this one intersection point. And then let's call the last one intersection normal. So now these 3 vectors will hold the intersection data for all the intersections that take place in our ray tracers. And so the intersection color will hold whatever the object color is that we hit, and then the intersection point will hold the exact location where the ray intersected that object. And then finally, the intersection normal will be for that exact point in space, what is the normal to the surface which that point sits on. So in the case of the plane, it's super easy. We'll just copy the plane's normal that we defined ourselves, and that's a normal that's pointing straight up for the ground plane. But if we hit a sphere, we're going to have to do some extra work and actually calculate that normal at that exact point on the sphere. And once we get that, we'll assign it to this intersection normal. Okay, so now let's scroll down to where we do the intersection tests. And I'm going to move this over just a little bit. So let's handle the plane first because that's slightly easier to do. We don't have to calculate anything. We already have the surface normal. And so we're going to take out this pixelColor.mix because we're no longer just simply setting the pixel color to whatever the plane color is. That's too simple. That's not applying any lighting or shading. That's just a uniform color. So we're going to remove that. Now we do want to keep this nearest t equals t. That's also kind of its own running record as we go from pixel to pixel. And now that we have that winning t value, we go ahead and record some intersection data that we can use later when we're applying lighting and shading. And so let's record the intersection normal. And that's easy in this case because we already have it. It's called the plane normal. So now let's call our intersection normal and just simply copy. So dot copy, opening parenthesis, and that takes another vector, and we're just going to fill in plane normal for the parameter here. So plane normal, and then semicolon at the end. And so we just supply the plane normal to this copy function, and now intersection normal holds that intersection data. And now likewise, let's record what color this object is. So in the case of the plane, I think we use the word ground color to describe its color. So let's go on the next line and fill in the data for the intersection color at this particular location. So intersection color. And then likewise, we're going to copy whatever we have for this object. So dot copy, opening parenthesis. I believe we used the name ground color. So type ground, yeah, there it is, ground color. And so now end that with a semicolon as well. So far as the plane is concerned, we have everything that we need to apply lighting and shading at the end of the ray tracing operation. And so we have an intersection normal, so that N vector, remember from the earlier whiteboards. We have a color of the object, which is the ground color. And then we have the L vector, which is the direction to light vector that we defined ourselves. So we have everything we need to shade the ground plane now. So now let's scroll up to where we're intersecting the sphere, and likewise erase pixelColor.copy. So we're no longer doing that simple solution that just lighted up the sphere with its own color. That's not really realistic. And again, keep nearest t equals t, because we need to have that nearest t being the running record of the closest t value that it found for this particular array. Okay, so unlike the plane, now we do need an intersection point for this sphere. If we hit a sphere, we do need that point out in space where the ray actually hit the sphere. And we need that to be exact because we're going to use it to calculate the surface normal. And so let's call our intersection point. Intersection point. And we're going to use our new function that we just added called getPointAlongRay. So let's type dot and then getPointAlongRay, and it should pop up. Now that's a function, so it needs parentheses, and so opening parentheses, and it reminds us that it needs a ray origin, a ray direction, and a t value for that ray in order to get the point back that you want. So let's supply it with all that information. So ray origin, comma, ray direction, comma, and then the t value. So just type t. So now it has everything it needs to do its work, and it should provide a nice intersection point out there in 3D space. And that'll be saved in this intersection point vector 3. So that was a statement in JavaScript, so we end that with a semicolon. Let's go on to the next line. And now we're going to begin to work with our intersection normal. We're going to start calculating it now. And so step one is we have to set the normal to the point that we just got back. And so let's set intersection normal to intersection point. So let's copy it, copy, and then intersection point, and then semicolon. So recall back on our first whiteboard that in order to find a normal vector to the sphere at this location, we simply take the point and subtract off the sphere center. So far in our code, we've done intersection normal equals intersection point. So we've done that. That was our copy operation, remember? So we did intersection normal dot copy intersection point. And so that is like saying n equals p. And now we just have to subtract off the sphere center. Let's go back to the code. So all we need to do is subtract off the sphere center. What we said here is n equals p, so intersection normal, copy intersection point. And now we just take that normal and subtract the sphere center. And the sphere center, I believe we called, let's check real quick, sphere position. So we didn't name it sphere center, but it's the same thing. So we need to subtract off sphere position, and that's the center of the sphere itself. Let's go back down here and type intersection normal dot subtract And we have that handy routine already written in our vector 3 libraries. So subtract, and then that's a function, so it needs parentheses, open parenthesis. And then it reminds us it takes another vector, and we're just going to subtract off the sphere position, which is the sphere center. So sphere position, semicolon at the end. And at this point, we have a normal vector that's pointing in exactly the right direction. Now, the last thing we needed to do, remember, was normalize this vector. But if you remember from when we added normalize to our vector 3 libraries, let's go check that out real quick. So in math utilities, if you go to normalize, that uses the vector length function. And if we go to vector length, we realize that that uses a math.square root. And the square root operation is pretty expensive. Even on today's blazingly fast machines, you want to kind of avoid square root. Remember, we're doing this for each and every pixel on the screen, and that could be millions of pixels. So we'll essentially be calling this square root function a million times. So go back into diffuse lighting.js and kind of follow along with me here on this scenario. So let's say we do call that normalize function that has the square root in it. So let's say we did that on the next line here. Now, reading from top to bottom, let's say the ray hits the sphere, and we go ahead and fill in the data for this intersection. And also we go ahead and normalize that normal vector so it's a unit length of 1. Well, that's great, but continuing on, let's say if we intersect something else like the plane or another sphere, well, then we would have normalize in here as well. And then continuing on, if we had more objects, we would do normalize, normalize, normalize. So potentially we could have several calls to normalize, which involves the square root operation, which is expensive, on every single object. And so why do that if it's just going to get overwritten anyway? So you don't want to do it on an object by object basis. If you find an intersection, that's great, but don't do the normalize yet. Save the normalize until the very end when we have the winning t-value and we've looked through all the objects in the scene. And only then do we do the normalize function that has the expensive square root in it. And so I'll show you what that looks like in a moment. And now all we need to do to finish up with this intersect sphere data filling is just to fill in the data for the color. So let's fill in the data for the intersection color. So type intersection color, we'll click on that, and then we're just going to simply copy, so .copy. And I think we had named it sphere color, so whatever color this sphere is that we defined earlier. So sphere color, yes. So it pops up there. And now semicolon. And that concludes the sphere part now. So we have everything we need to do shading once more. So we have a intersection normal, and we have an intersection color, and then we've already defined the light direction vector earlier, and that's all we need. Oh, and one housekeeping thing that I forgot is that we should go up here and reset pixel color to black for every pixel. And so go up where it says nearest t equals infinity. And remember, we had put this in last time, important, must reset nearest t for each pixel. Otherwise it messes up as you go from pixel to pixel because it keeps using that old stale value for the nearest t. So likewise, as we go from pixel to pixel, we have to reset the pixel color to black. And that way each pixel starts with a fresh nearest t value here as infinity, and then it starts with a fresh pixel color of nothing or black. So 0, 0, 0. So let's do that here. So go on the next line below nearest t equals infinity and type pixel color dot set. That's a function and it needs parentheses, so open parenthesis, and it reminds us that it needs an x, y, z components. And in this case, since it's a color vector, we're interpreting those as R, G, B. So let's set it to no color at all, so black. And so that'll be 0, 0, 0. So let's do 0, 0, 0. And then semicolon. And so now each pixel, as we go from pixel to pixel and do the ray tracing through each pixel, it'll start with a fresh copy of nearest T, and it'll start with a fresh copy of pixelColor. So that way it won't pollute the next pixel down the line. Now, if we go check on the progress of our demo at this point, it won't look right because we're not really doing any lighting yet. But let's just go see what happens when we go check on the demo. Oh, interesting. So we have the sky working out correctly, but then where it hit the sphere, we have no color, and where it hit the ground plane, we have no color also. So let's go back into the code. And that's because here we're setting the intersection data, and that's great, but we're not setting the pixel color to anything. The only place that we're setting the pixel color is when we miss everything and nearest T equals infinity. And remember, that means when the ray didn't hit anything at all, it just went into the background. And so we just copy the gradient sky color, and that produces the sky in the background. So that's all we can see because we just did the pixel color. So now we need to assign the pixel color using this intersection data that we got before. And so I want to add a code block here between intersect plane and nearest T equals infinity, right between these two code blocks, because now we need to check if the ray did hit something, then we need to light and shade that particular intersection. Go after the closing curly brace and hit enter a couple times. And now, how do we check if the ray hit something? So over here we have if the ray missed everything, nearest T should equal infinity still. So it went forever and it didn't find anything. But how do we know if it did find something? Well, the T value that we got back, the nearest T, will be less than infinity. So if it hit anything at all in the scene, so a sphere, plane, cube, whatever you put out there, your nearest T will now be less than infinity. So I'm going to scroll up just a little bit. And now let's do an if statement here. So if, opening parentheses, nearest T is less than infinity. So this will only happen if the ray hits something out there and we got a T value back that's less than infinity. And that means we got a positive hit. So go on the next line and then open curly brace and it'll close it for you and then enter. And I'll go ahead and add a couple of comments here so that it's clear what we're doing. Okay, so I added these comments here, and so this says if the ray hit anything at all, apply lighting to the intersection using the recorded intersection data. And that's when nearest T is less than infinity. Now, if the nearest T is still infinity after we check all the objects in the scene, that means it missed everything. So if the ray missed everything, set the pixel color to the background color. And so we just copy the gradient sky color in this case. Okay, so finally we're ready to add the meat to this demo and add the important diffuse lighting that we've been talking about all this time. It's finally time to add it to our scenes. And I promise it's going to be worth the wait. So the first thing we do in this code block where nearest T is less than infinity, and we did indeed hit an object, is we have to make sure that the intersection normal is normalized to a unit length of 1. And so remember, we didn't do that when we calculated the intersection normal for the sphere, and we just simply copied it in the plane's case. So right away we call intersection normal dot normalize. Normalize the normal. And in fact, that's a good saying. It's funny to say, but really, you have to have all your intersection normals normalized themselves. So although it makes for a funny phrase, you must normalize your normals. Because remember, when we do the lighting calculation, we do n.L, and that only equals cosine theta, which is the Lambert's cosine law, if the n and L are unit vectors that have been normalized already. So we must normalize all the normals. Normalize, and then that doesn't take any parameters, but it's a function, so it requires parentheses. So opening parenthesis, and then just go to the end and type semicolon. And so this is the more performant way to handle the intersection normalizing, because if we did that every time we calculated it for all the objects out in the scene, then we would be wasting resources by normalizing that surface normal each and every object, which might get overwritten anyway if the ray finds a closer object that it hit. It'll just make your ray tracer a little slower. So in this way, we save the normalize to the very end, where we only do it when we absolutely have to. Now we can go on the next line. And so since we're doing diffuse lighting today, let's call our diffuse color and assign to it whatever intersection color we got back from all of our ray object intersection tests. So diffuse color, let's simply copy, so dot copy and then opening parenthesis. And let's copy this intersection color that we had previously recorded as our intersection data. So intersection color. And then semicolon at the end of that line. Enter. And real quick, let's go back to the whiteboard where we saw the final equation to add the diffuse lighting to all of our objects. And so let's go back to that whiteboard real quick. And so we're just going to look at this final equation here. So it says to get the correct color for your shaded object, you need to take the color of that object, which we have, that's the intersection color, times the light color, so whatever RGB that is. So let's do that now. We've already set our diffuse color to the object color, so diffuse color dot copy intersection color, so that handled that. Now we need to multiply that diffuse color times the light color. So let's go do that. So diffuse color. Now we get to use our multiplyColor function that we just added to our vector3 library. So multiply color. And that is a function, so it needs parentheses, open parenthesis. And now it's helpful that we renamed this, so it reminds us it needs another color vector, not just a typical 3D vector, but actual color vector, because it's going to do a straight multiply, x times x, y times y, z times z. Or in our case, as we're interpreting this, r times r, g times g, and b times b. So now we want to multiply against the light color. So let's type that. And I believe we called that sunlight color. So type sunlight, there it is, sunlight color. And now semicolon. So at this point, we have part of that equation done. And let's go back and look at it real quick. So far we have the final diffuse color equals the intersection color or the object color times the light color or our sunlight color. And now we just need to calculate this n.L. And then once we do that, we multiply that with whatever we got over here. So let's do the n.L now, and then we'll take that result and multiply it with the diffuse color. So let's do the dot product now between the surface normal and the light direction. And real quick, up here, we had called this variable diffuse intensity. So that will hold the number that we get back from the dot product that we're about to do. That diffuse intensity will tell us how bright to shade the object at that point on the object. and we'll use that variable name. So diffuse intensity equals, now we take the surface normal that we've recorded and now normalized, so it's unit length, and then we're going to dot that with the light direction vector that we defined earlier. So let's take the surface normal, and that was recorded as the intersection normal. So intersection normal dot, and then the word dot, because we're doing a dot product, and that's a function, so opening parenthesis. And it reminds us it needs another vector as a parameter. So what do we want to dot with? So we want the normal dotted with the light vector. And I believe we called that direction to light. So that means which way is it to the light? So direction to light, and then it should pop up. And now semicolon to end that line. So now we have successfully got the diffuse intensity for the object at this location. So you can see by this code that we don't really care what object it was that got hit. So we could have hit the plane, or we could have hit the sphere, or we could have hit a cylinder or a cube. It doesn't matter, but all that matters is that we have that intersection data. So the intersection normal, intersection color, and the direction towards the light, and the light color itself. That's all we need. Now there's one thing that I forgot to mention with the dot product and doing the cosine law, and that's if the vector n and the vector L are pointing at more than 90 degrees from each other, you'll actually get back a negative number as your intensity. Well, a negative intensity doesn't really make any sense in the physical world, so we're only interested in 0 to full intensity. And in other words, 0 to 1. And so 0 being that it's 90 degrees from each other, and 1 meaning they're both pointing in the same direction, and it should be maximum intensity. So we're only interested in values from 0 to 1 and everything in between. So let's clamp this intensity now that we have it and make sure it's a positive number. So how you do that in JavaScript is go on the next line and call diffuse intensity again equals, and then we're going to use the math object in JavaScript. So that's capital M math dot, and we're going to call its max function. So maximum, M-A-X, and then that's a function, so it needs parentheses once more. So we do opening parenthesis. And now for its parameters, it takes 2 or more numbers, usually 2, and it compares those, and it'll return to you the maximum of those 2 numbers. And so we want the maximum of 0 and whatever diffuse intensity is. So diffuse intensity. And then finally a semicolon. So this ensures that diffuse intensity is a positive value. So let's say diffuse intensity is 0.7. Okay, so that's fine. We can use that value. So when you get here, it says, what is the max of 0 and 0.7? Well, 0.7 wins in that case. And so diffuse intensity equals diffuse intensity. So it just leaves it alone and does nothing. But let's say the normal is pointing like way away from the light source, and we get back a negative number. So like negative 0.5. And so when it gets to here, it says, what is the maximum between 0 and negative 0.5? Well, 0 wins in that case. And then it sets diffuse intensity to 0 in that case. And so it kind of clamps that diffuse intensity value to a positive number. And that ensures that we'll get only meaningful results from our diffuse intensity calculations. Okay, and then let's return to the whiteboard once more. And all we have left to do is multiply that diffuse intensity, this n.l that we just did, with what we have as our diffuse color. So the diffuse color is the object color or the intersection color times the light color times the intensity. So now we can just take what we have so far for all this and scale it by this number, or a scalar number. Because remember, the dot product returns a single number. So if we want to scale a vector by a single number, we have to call the multiplyScalar function on our 3D vector. And so let's do that now. So we were working with this diffuse color here, so let's call diffuse color dot, and then we're going to call the multiplyScalar function. So multiply, and then it pops up here. This will multiply that vector with a single number. So it's a little different than what we did up here, which is multiplyColor. That we did x times x, y times y, and z times z. But this one, we're going to do x times a scalar, y times a scalar, and z times a scalar. And in each instance, that scalar is the same number. So x times a number, y times the same number, and z times the same number. And what is that number? That is diffuse intensity. So opening parenthesis, and it reminds us that we need a scalar number, not a vector. So just a simple number. And we have that as diffuse intensity. That's our number that we just calculated with the Lambert's cosine law. So diffuse intensity. And then that was a statement, so semicolon. And now that completes everything we have to do to get diffuse lighting. But still at this point, if you go and check the demo, all the objects are gonna be black still because we haven't set the pixel color to anything yet. So let's go see if that's the case. Yes, so everything's still black, and all these equations we did and all our lighting calculations and normals and normalizing and all that was for nothing. Oh gosh, but we're about to fix that with a simple one-liner. So all we have to do is set the pixel color for these pixels to be whatever we calculated for the diffuse color. So let's go do that now. So hit enter a couple of times. And actually, I'm going to do something here that may seem a little weird. Instead of just copying the pixel color, copy diffuse color, we're going to say pixel color add diffuse color. And so I will explain that more in detail on the very next episode when we talk about specular lighting and Phong lighting. We will take a look at the Phong illumination model, and that models the total light output of your scene as ambient color plus diffuse color plus specular color. So right now we've calculated diffuse color, and so we can just simply add that to the pixel color. Now the pixel color is currently black, right? So when we looked at our objects just a moment ago, they're all black still. They have a value of 0, 0, 0. So now if we add the diffuse color to that, it'll just add it into that black pixel and then make it whatever color we want. So although it may seem weird that I'm saying add this color, it's because of what we're going to do in the next episode when we add in specular color. We'll have to sum everything and we'll have to add up all those components. So the ambient, the diffuse, and the specular, and then we'll simply add those to the pixel color, which is black to begin with. And so that'll produce the final light and color output for our scene. So now let's finally call pixel color. And this is the magic line. This is what will turn everything on. So pixel color dot add. We could have done copy here, but we're doing add, and I'll explain that on the next episode more. And then it's a function, so opening parenthesis. And we're simply going to add the diffuse color that we've just calculated. So diffuse color. And then semicolon. Okay, are you ready for the moment of truth? So when we look at the scene now, we should have diffuse lighting on all the objects, the plane, and more importantly, the sphere. And we should see a gradient color going from the brightest portion of the sphere around the side to the back where it should be no light at all or black. So let's check out our new demo. Whoa, isn't that cool? So hopefully this convinces you that we're really ray tracing in 3D, because now we can tell that this is a ball or a sphere shape and not just a flat circle like it was before. And just like the tennis ball that had the light over here and then gradually getting dark and then to maximum darkness over on this side that's not facing the light. And so if we look at our scene, we have maximum brightness here where it's facing the light directly. And then as we rotate around the sphere's surface, we get darker and darker and darker. And finally, there's no light reaching the back of the sphere. And that looks much more realistic now. So looking at this image, one thing that we took out before was the little fog calculation in the background of the scene, like right where the plane meets the sky. And so we're missing that nice gradation from the ground to the fog color. And so we can simply go ahead and add that back in if we want that nice fog in the background. So let's go ahead and do that. So let's go right here and click enter a couple times. And now how we did that, if you recall, is pixelColor dot mix. We're going to mix between the object color and the sky color. So mix, and that's a function, so opening parenthesis. And it reminds us that it takes a vector A and a vector B and a t value to mix between them. So the t can be anything from 0 to 1. If t is closer to 0, it'll mix in more of the vector A. And if t is closer to 1, it'll mix in more of the vector B, and everything in between. So you can have a nice linear interpolation between those two vectors. And those vectors can be anything. They can be direction vectors, or in this case, color vectors. So we're just going to mix the colors together. So let's take the pixel color itself. So we've already done the work and calculated this nice pixel color here. So let's use that as our base. So pixel color, comma, and then what do we want it to fade into? Well, we want it to fade into the sky. So let's call the gradient sky color. That's what we had named it. It's that bright blue color with the light gray color as you get to the horizon. And now, comma, and what is the t value? How should we mix these two? Well, we had said that the distance that the ray had traveled to reach that object should be the t value. And that way, if the t value is really close, we won't get any fog. But if the t value had to go a long way for that ray to hit the object out in the scene, like way in the background, then that t will be much closer to 1, and it'll lean towards this gradient sky color more and more until finally it's total gradient sky color if you get far enough in the scene. So let's use the nearest t value that we got. So nearest t. And then we had multiplied it with a small number. So I like to change that number just slightly. And this is purely through experiment. So I've tried different numbers out there, and this particular number seems to work pretty well. So times 0.004. And that's a really small number, but remember the t values can get really big as you get to the back of the scene where the plane kind of fades off into the distance. Those t values might be in the thousands. And so we have to multiply this t value by a really small number in order to keep this mixing value here in the range of 0 to 1. And like I said, this 0.004 is just through experimentation. So feel free to try some other numbers on your own and see how it affects the fog distance. And now that was a statement in JavaScript, so we end that with a semicolon. And let's go take a look at the effects of that line. All right, great, we got our fog back. So as you can see, the ground fades nicely back into the horizon. And as you get right on the horizon, it becomes the gradient sky color, and then it transitions from a misty gray color up into the bright blue of the sky. That looks much more pleasing to my eyes, seeing it fade into the distance like that. Okay, so there's one more thing I want to add to this demo. And remember when we were taking a look at real-world diffuse objects, and so like this tennis ball, and if I turn off this light over here, this fill light, now there's only one light source in my room here, and so it's coming from this direction. But you can see that even though this side is maximum brightness, as we get around to where the sphere can't see the light anymore, we can still see the object back here. It's not completely black. And recall that we had attributed that to the ambient light of the room, or the global bounce lighting that's happening all around us. And so there's only one light source in my little room here, but it's shining on the wall and the door back there and on the floor. And all that is reflecting the light back this way and illuminating this sphere or this ball from this side, so you can actually see the sphere on the dark side. So if we take a look at our image here, as we go from the light side to the dark side, it's completely dark over here. It's a color value of 0, 0, 0. And in reality, there would be some bounce lighting coming off the ground and reflecting back on the sphere from the bottom, where even though it can't see the light source directly, it's still being illuminated just a little bit. And so many years ago, it was probably the 1960s, computer graphics researchers added a kind of a cheap solution to this, and it's kind of a hack, but it's called ambient light. And so rather than trace the rays all throughout the room and find out what light is bouncing off of what surface and coming back onto the backside of the sphere, they just add a global ambient light to all the objects in the scene. And that way it'll increase the lighting on the dark side of the objects just a little bit, so you can see that there's an object there and it won't be completely pitch black. And so let's add that into our ray tracers. And the good news is ambient light, since it was developed so many years ago, it is the easiest type of lighting to add to any scene. Literally, it's just like a couple of lines of code. So let's go add that now, and it'll make a big difference though. It's well worth adding. So let's go back into the code and scroll up to where we define diffuse color. And now let's go right above diffuse color and just hit enter. And now we're just going to add an ambient color. So let ambient color equals new vector 3 that we're interpreting as a color vector. And we're not going to define this right now. We're going to actually fill in the value later where we do the diffuse portion. And speaking of ambient light, I forgot my fill light over here. So let me do that and get some more ambient light on my face. Ah, much better. And just as we did for diffuse color, we added a diffuse intensity. Let's add a variable called ambient intensity. So go on the next line, let ambient intensity. Now in this case, since it's a global variable, so this ambient light is going to permeate the entire scene, we only have to set it once, because it's going to be the same for all objects out there in the scene. So we can actually define it right here and be done with it. So let's go ahead and set it to a reasonable value. Remember, an intensity is from 0 to 1, 1 being the maximum brightness and 0 being nothing at all. So let's just try like 0.4 or something. And we'll see how that looks. And then semicolon. So let's go down to where we had the diffuse lighting calculation. And click right here after intersection normal.normalize and hit enter a couple of times. And now we're just going to set the ambient color. So ambient color dot, and just like we did for the diffuse color, we're going to copy the intersection color. So whatever we hit out in the scene, we're just going to set the ambient color to that intersection color. So ambient color dot copy opening parenthesis, intersection color, and semicolon. Okay, and then just as we did with diffuse color, when we multiplied the diffuse color times the diffuse intensity, we need to do the same for the ambient color. So now we're going to do ambient color multiplied with the ambient intensity, and that'll bring it down to a reasonable level that'll act like a soft fill light. So go on the next line and type ambient color dot multiply scalar, because now we're multiplying it with a single number. Multiply scalar, opening parenthesis, and it reminds us we need just a pure number, so a single scalar number. And for that, we just put in ambient intensity, which we defined at the beginning of the program. So ambient intensity. And then put a semicolon at the end of that line. And now maybe hit enter just one time to separate these two color contributions. So this is the ambient color contribution to the pixel, and then this is the diffuse color contribution to the pixel. And as you'll see on the next episode, we're going to talk about specular lighting. And so as you can imagine, we'll have below this line here, we'll have a specular color calculation, and then we'll add that in as well. And that'll be the total light output for our entire scene. And so we'll have a mixture of ambient, diffuse, and specular. And so let's finally add in the ambient color to our pixel color, and everything should be lit now from all sides, no matter which way it's facing. So go right before diffuse color, and then let's call pixel color. And just as we added diffuse color, we're just gonna simply add ambient color. So dot add, opening parenthesis, ambient color. And then semicolon at the end of that line. And with that, I think we have everything in place. So let's go check our demo now, and it should have the diffuse lighting that we calculated, so the direct light that's coming from the sun. And then as you get around to the dark side of the objects that can't see the sun directly, then we'll have a nice ambient light that's like a global illumination type of light. And it'll provide a nice fill light for the side of objects that can't see the light source directly. So let's go check it out. Wow, that makes a huge difference, doesn't it? It's much more realistic now in its lighting, because you can imagine that when the sun hits the ground will reflect a little bit of that light back onto the bottom of the sphere that can't see the sun. And so we get that nice fill light on the other side of the sphere that can't see the light directly. It almost looks like you can reach out and touch that red sphere, doesn't it? It makes it just pop out of the screen in 3D. And so now you can see why those graphics researchers long ago in the 60s and 70s added this simple ambient light to their scenes. Because for a single calculation, remember, all we did was multiply it by the ambient intensity. You get a global fill light like this, and it makes your scene appear much more realistic, like how we see objects out in the real world. So now that we have a more realistic scene with diffuse lighting, let's have some fun and move the sun around a little bit and see how that affects our lighting. So let's scroll up to where we define the direction to light vector, and here it is. So currently we have it to the right and up and behind us. So now let's just simply reverse the X direction. So let's move it over to the left side of the sky. So -1, and see how that looks. All right, cool. It's working perfectly. So now we've taken the sun and just moved it over to the other side of our scene. And now this side is getting lit fully. And then as you go around the sphere along its surface, it gets darker and darker until we only get the ambient light. Let's move around the sun a little more. It makes you feel so powerful, right? Let's put it back to +1. And how about a little lower in the sky? So instead of 1, let's do like 0.3. And let's see what happens with that. Oh, cool. That's like a scene at sunset, right? So the sun is real low in the sky, and the sphere is being illuminated more on its side, and the left side of the sphere now is in shadow. Oh, and also notice that our ground plane got much darker, and that coincides with what we see in real life. So when the sun is right overhead, the ground should be like really bright. Picture a concrete sidewalk or a parking lot during the day. So as the sun is overhead, it gets real bright. But then as the sun sets, then that surface gets much darker because it's a grayish color. So let's make the X component 0 and the Z component 0, and then make the Y component, which goes up, a maximum value of 1. And now the sun should be right above us. And so let's see how that affects the lighting. Ooh, that's kind of cool. It's pretty dramatic. And notice how light the ground has become. So the normal of the ground is pointing straight up, and the direction to the sun is also straight up. And so those vectors now coincide, and they give a maximum intensity of 1. And so the ground is at the maximum brightness that it can be. So now let's just move the sun around a little more, and then we'll put it back to where we had it to finish out. Let's put the X back to 1, and we'll leave the Y as 1. And now, instead of 1 in the Z component, let's do -1. And so now that means that the sun is behind the sphere, shining down on it from that way. So it's a little farther out in the scene now, and it's going to be lit from behind. So let's go see what that looks like. That's pretty cool. So our human eyes are trained to look at objects like this and determine where the light source is just by how it's shaded and how it's lit on one side and shadowed on the other. And so we can tell from this image that the sun is directly up and to the right, and it's a little behind the sphere because it's being backlit. So now let's put everything back to what we had before. And so we have just 1s in every component. So X is 1, Y is 1, and Z is 1. And let's go check that. All right, I think that looks really cool. So we're going to leave it there for today. And so I really love the fact that you can do these simple calculations, because remember, all we did was a handful of lines of code for our diffuse lighting calculations. And we just did a simple dot product between the normal vector and the light vector. And in return, we get this really cool lighting effect for all the diffuse objects in our scene, which mimics what we see out in the real world. So that's why I think Johann Lambert's discoveries back in the 1760s and his famous cosine law of diffuse lighting is so awesome and profound, because by simply doing a couple of calculations, we get an image that has a lot more realism. And so on the next episode, we're going to add some highlights to a sphere like this and add the ability to have shiny objects as well as diffuse objects out in our scene. Now, one thing you might notice that even though this looks really awesome with the shaded sphere and the shaded ground, is that it kind of looks like it's floating over the ground. There's no shadows. And so in a future episode soon, maybe in 2 or 3 episodes down the line, we're going to take a look at how to do shadows and cast shadow rays towards the light. And so that'll produce the nice shadows underneath the objects that sit on the ground. And then it'll look even more 3D because we'll have those shadows as depth cues, where we can tell if an object is sitting on top of another object. So if you think this looks cool now, wait till we add specular lighting, reflections, refractions, and shadows. And so I think you'll be amazed at how little code we need to add all these cool features and make our scenes even more realistic. All right. Well, I hope you enjoyed adding diffuse lighting to our scene today. as well as learning a little bit about the history and theory behind Lambert's cosine law and how we can use that simple yet profound law to correctly light and shade the diffuse objects in our scenes. And as I mentioned a moment ago, on the next episode, we're going to take a look at specular lighting. And specular lighting produces those bright highlights that we see on shiny surfaces. So I'm really looking forward to adding specular lighting to all the shiny objects in our scenes next time. And until then, have fun with the diffuse lighting that we did today, and maybe experiment with moving the direction of the sun around as I was doing before, and maybe try changing the color of the ground plane or the sphere or even the sunlight itself, and see how making those small changes to the colors affects the final lighting of the scene. So try some stuff out on your own and have fun with it, and I'll see you on the next episode.